Hello guys, welcome back to my channel Engineering Chronicles of Plant Design, and today's video is a continuation of design of a pressure vessel as per ASME section 8 division 1. So in today's video we will be watching you'll be learning about the formulas of how to design a shell of a cylindrical shape, spherical shape, hemispherical, dished, spherical dished, elliptical dished, conical, conical dished, and a spherical shape shells. So, what are the formula and criteria to use those formula as per section of division 1 that we are going to see in this today's video. So, before we go into the formulas, so you should know what are the different type of stress involved in a shell when there is an internal pressure. So, today's video is all about thickness design of a pressure vessel only due to internal pressure. So the design with the external pressure we will see on later in the later video. So when there is the internal pressure, there are two kind of stress normally involved. So first is circumferential stress. If you see here, circumferential stress is if it's around, that is a circumferential stress, and there will be a longitudinal stress. Okay, so our formula is a combination of both, and you have to use the maximum thickness value obtained from both these formulas. So, formula to design a cylindrical shell, it is mentioned in UG 27.1 that TC. So, TC is the thickness due to circumferential stress is PIR divided by SE minus 0.6 PI. So, what is PI? PI is internal pressure, R is the radius, S is the allowable stress value. This you will get from section 2 part D. Okay, and E is the efficiency which we have seen in the previous video. Depending upon your radiography inspection, efficiency of the inspection is defined, and based on that we will put this as 0.7 to 1 range, 0.7, 0.85 or 1 depending upon the radiography which you have chosen, minus 0.6 pi. Okay, so here you have a condition. The condition is if your internal pressure is less than equal to multiplication of 0.385 times of S into E. So allowable stress and E. Check this factor. If your internal pressure is less than this value, then you go with this formula. Otherwise, if your value is more, if your internal pressure is more with this value, in that case you have to use mandatory appendix 1-1 formula, that is Tc is equal to R exponential power of Pi divided by Se minus 1. So Pi is internal pressure, S is the allowable stress, and E is the joint efficiency. So this is a circumferential thickness due to circumferential stress. So moving on, thickness required to handle longitudinal stress. So that here also we have a condition. If your internal pressure is less than equal to 1.25 times of S into E, that is allowable stress, and joint efficiency multiplied by 1.25 time, and this value is less than the internal pressure, that in that case you have to use UG 27 to this value, or your internal pressure value is more. In that case you have to use the formula as TL is equal to R square root of Z minus 1. So Z, the value of Z is equal to Pi by Se plus 1. Okay, so Pi by Se plus 1. So this will give you the thickness due to longitudinal stress, and that is the minimum thickness requirement. So as per UG 16, so minimum requirement is 1.5 mm. In that means none of the pressure vessel can have a thickness of a shell which is less than 1.5 mm. It has to be 1.5 mm minimum. So when you have all this value, so the thickness of the cylindrical shell excluding corrosion allowance is equal to T is equal to maximum of circumferential value, longitudinal value, and 1.5 mm. So for example, here you have used this UG 27.1. and TC you have got 0.8 mm. I'm just saying example 0.8 mm, and here you have got 1 mm, and 1.5 mm is the minimum requirement. In that case, your thickness will be 1.5 mm. Okay, but if your client has a adherence and he says minimum limit is set as 4 mm, then you have to go with the 4 mm. Okay, but in a case if you have more than 4 mm and your client says 4 mm, so you have to go with more than 4 mm. That is because he is saying only minimum value, not the maximum value. Correct. So this is due to the from the cylindrical shell. So moving on, next is the MAWP. So what is MAWP? MAWP is maximum allowable working pressure. Okay. So now we have found thickness, that is T, mm, that is 5 mm, 10 mm, whatever we have received. So based on that, in accordance to thickness of the shell, your MAWP will be described. So for example, here also we have a range. If thickness is less than or equal to r by 2, r is the internal radius. In that case, you have to use 27 UG 27.1 MWPC for circumferential stress value. And if your T is more than r by 2, in that case, you have to use appendix 1-2. So MWP C will be S into log E of r plus T by T. Okay. And then again, for the longitudinal stress, you have to use, if T is less than or equal to r by 2, in that case you will use UG 27.2. MAWP will be described MAWPL. Again, if your T is more than r by 2, so use the appendix 1-24 formula. MAWPL is equal to SEZ minus 1 and Z is equal to r plus T by r the whole square. Okay. And in the MAWP case, we will not take the maximum, we will take the minimum. The lowest MAWP will be your MAWP which is acting on the shell. So earlier we have said cylindrical shell, right? So what if we have a spherical shell? So spherical shell, you are aware, right? This is just this is the spherical shell, round shape. So this spherical shell is mostly used when you are storing natural liquefied natural gas, LNG, LPG. So this kind of shell is normally used. Okay, because this has potential to uh, sustain high pressure. Normally bullets can be spherical and hemispherical dishes, but the storage for storage tank, so a local storage tank above the storage tank of a gas is used to be a spherical shell. So for spherical shell, the formula is, if your internal pressure is less than or equal to 0.665 times of SE, so in that case you use the formula UG 27.3. T is equal to Pi R divided by 2AC minus 0.2 Pi. Okay, R is the internal radius. So this this so this is R. This radius is R. Okay, don't watch my drawing, it is very ugly, but just for the identification, this is R. Okay, and then divide by 2AC minus 0.2 Pi. Okay, that is the formula as per, if we if we if we have internal pressure less than this value. If Pi is more than this value, in that case you use mandatory appendix 1-31. That is 3 is equal to internal radius R multiplied by exponential power of 0.5 Pi divided by SE minus 1. Okay, and then you come back to the MAWP of a spherical shell. So MAWP is maximum allowable working pressure. If your thickness of the shell is less than or equal to 0.356 R, in that case you use UG 27.3. So MAWP is equal to 2 into SET. T is thickness, which we define from here, that you have to use here, divide by R minus 0.4 T. Okay, and else if your thickness is more than 0.356 times of R, in that case you use mandatory appendix 1-3 MAWP is equal to S into E multiplied by log E of R plus T divided by R. Okay, So this is the formula which is used for spherical shells. So moving ahead, formula to design ellipsoidal head. Okay, ellipsoidal dish head. Here, this is ellipsoidal dish head, thickness, height of the dish head, and this is internal diameter. Diameter or d by 2 is r. Okay, so in this case, you you define the aspect ratio beta. Beta is equal to d by 2h. Normally, whenever you design the ellipsoidal dish head, h is normally taken as 1/3 of d. Always h is taken as 1/3 of d. But in some case you will be knowing the aspect ratio beta. In that case, you define h by d by 2b. Your client will define sometimes the ratio of the aspect ratio beta. In that case, you will redefine the value of h given is equal to internal diameter divided by 2 beta. Otherwise, you will find the beta value of beta, which is internal diameter divided by 2 into h, and h is normally taken as one third of diameter for ellipsoidal. Okay, so factor k of ellipsoidal is obtained. K is equal to 1 by 6, 2 plus beta square. Okay, and using this value of K and using the equation appendix 1 dash 4 1, the thickness for ellipsoidal dish head is given by T is equal to Pi internal pressure into dk divided by 2AC minus 0.2 Pi. Okay, so K, you will get value K from here. D is the internal diameter, Pi is the internal pressure, S is the allowable stress of the dish of the head. Okay, of the head material, not the shell material, of the head material. In some cases, you may have different shell and head material. Okay, the client will say you use different separate shell and head material. In that case, the allowable stress value will be different and minus 0.2 pi. Internal pressure will not change. Internal pressure will remain same. Okay, so using the equation appendix 1 dash 41, the MAWP can be defined for ellipsoidal dish head as MAWP is equal to 2 times SET divided by KD plus 0.2 times T, or thickness which you receive from here. So K will be same, K will not change. Okay, so your MAWP will be redefined based on the thickness which you have received. So moving ahead, formula to design of toruspherical dish head. Toruspherical dish head, here you have knuckle radius. So in ellipsoidal we don't have knuckle radius, but in toruspherical dish head we have knuckle radius, and we have D, that is internal diameter of the dish head. This is same as the internal diameter of the pressure vessel. L, so L is the radius of this. L is the radius of inner crown radius. This is called inner crown. Okay, we have mentioned here L is the inner crown radius. Okay, and R is the knuckle radius. This is knuckle radius. So here you have to define M first. M is equal to 1 by 4 3 plus root of L by R. Once you define M using the formula of appendix 1 dash 43, you will find thickness of the toruspherical dish head. T is equal to Pi Lm divided by 2 minus 0.2 Pi, and thickness which you receive from here, you will redefine the MWP as 2 times SET divided by Lm plus 0.2 T. So whatever L you have received here for this thickness, same you will use here, and MWP you will receive. Okay. So moving on next, design of the hemispherical dish head. So hemispherical dish head, this is hemispherical dish head, internal diameter, thickness T, and this is L. Okay, L is also a crown radius, similar to d by 2 also. Okay, so here I've given you inner radius r equal to d by 2, outer radius r plus t. Okay, if you are doing the calculation with outer radius, so in that case r0 will be equal to r plus t. So thickness of this hemispherical dish head, here we have condition if pi is equal to less than equal to 0.665 SE. In that case, you use UG273 formula, that is T is equal to pi r divided by 2AC minus 0.2 pi. Else, if pi is more than 0.665 SI, then use mandatory appendix 1 dash 3 1 T is equal to r multiplication of multiplied by exponential power of 0.5 pi divided by AC minus 1. This formula is same as a spherical dish head. If you go back and check, almost same as a spherical dish head. Okay, and MAWP is also, we have factor T if the thickness T achieved from this formulas is less than or is equal to 0.356 R. So using UG273, you will use MAWP to define as MAWP is equal to 2 into SET divided by R minus 0.4 T, or else MAWP is equal to 2S. S is the allowable stress value of a material you have used into E. E is efficiency log E of R plus T divided by R, same as a spherical 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 shell. Okay. So moving ahead, it is conical head. If you have a conical head, in some cases you will be designing a xylo where you have a conical head, but here this is called semi apex angle, and this semi apex angle should not exceed 30 degrees. Okay, just make a note, whenever you're using a conical, don't use this semi apex angle more than 30 degree. Okay, try to maintain within 30 degree. In that case, you can use the mandatory appendix 1-45 formula. T is equal to pi d divided by 2 cos alpha multiplied by SE minus 0.6 pi. So alpha is a semi-apex angle, and MAWP defined with the thickness which you receive here will be equal to MAWP is equal to 2 into SE T cos alpha, T thickness received from here, divided by T plus 1.2 times T into cos alpha. Okay, that is conical Richet formula. So moving ahead, formula for design of toric conical. So toric conical is a combination of torispherical and conical. Okay, torispherical and conical. So hence we always use two thickness formula. So T for this arrangement thickness will be you are defined by two formulas, that is appendix 1-43. This is torispherical formula, and 1-45 this is conical formula, and here you will get T as maximum of T knuckle, this is called T knuckle, and T cone, this is T cone and this is T knuckle. So whatever maximum you have received, that will be the max thickness of the toric conical dished. Okay, so depending upon the thickness, you will redefine the MWP. Same, you will have MWP for knuckle radius, knuckle area, and MWP for conical area, and that will be same as the torispherical dished formula MWP and conical dished formula MWP, and minimum of this both will be the MWP for that particular dished. Okay, so I hope you have enjoyed this video. Uh, so please don't forget to like, share, and subscribe to my channel, to my video. Like my video, please share it. There will be a person who is in a dire requirement to know about ASM section division 1. This is a knowledgeable video. Please share it. Let people know about it. Let people start working on the design of pressure vessel. If you have any doubt, please give a comment. And have a nice day. Thank you.